Friends, we are back here to continue with fluorescence spectroscopy. Now, in our last lecture, we started with what is called spectroscopy, and I mean discussing about what is spectroscopy and their types. So, today we will also continue to that. Now, we ended at in our last lecture we ended at this quantitative approach in spectroscopy, that is Beer's law. Okay, so Beer's law is the law which connects with the amount of light, that is it is a quantitative connection of the amount of light that is absorbed when some light, of course it is say UV visible, when it or maybe in some other cases also, maybe in IR also, when some radiation, basically we should say that some radiation passes through some medium with which this radiation interacts. Okay, and this radiation matter interaction takes place only and only when the energy levels associated with the molecular system or the system of interest, okay, these energy levels associated with the molecules or the system interest that match with the radiation energy present, I mean frequencies present. So, this Beer's law is basically A is epsilon lambda Cl, C is the concentration, L is the path length, and this is a characteristic constant of the molecule. Okay. As I told you in our last lecture, that if we know this epsilon lambda, then we can find out the concentration, unknown concentration from some standard graph. From some standard graph, okay, provided this length is same. Okay. Now, so what is actually happening in Beer's law? That you have got a light source, okay, you have got a light source, you have a slit. So, this light is coming out of this source like say maybe a tungsten halogen lamp or maybe a deuterium lamp. Then there is a slit which controls the amount of number of photons that should be allowed to fall onto your cell. Cell means the sample. It is optical cell, or it is sometimes it is called cuvette. Okay. After it passes through the sample, its intensity is altered. Intensity means this light source that may have a single frequency or it may have a number of frequencies. Okay, it may have a number of frequencies. So, in a detector, what it does is how much of light is absorbed, light intensity, and then it convert, then this detector signal is fed back to this formula, and then corresponding A values are obtained. Okay, A values are obtained, then you can plot A versus something, A versus say concentration, or maybe A versus some wavelength. Now, this is basically a typical, very typical simplified diagram, simplified schematic for an absorption spectrometer. Okay. The question when it is the question of absorption spectroscopy, we need to have some spectrometer. As I told you, spectroscopy relates to spectrometer and spectra. Okay. So, that means you have your source of light, this is your source of light, light is coming out. Okay. Then you have, maybe you have some, you can put some monochromator. Okay. Then you have some slit, okay, and then you have sample, although here monochromator is not shown over here, because monochromator is used to select certain frequencies. If you do not have a monochromator, means you allow all the frequencies to pass through the sample and then detector will maybe manage. So, this is your sample. Then you have got this side, you have got a detector. So, detector measures the signal, I mean measures the amount of light that is falling on it, and then comparing with a blank, I mean in one instance you put your sample, in the other instance you put a blank. Blank means the solvent without your compound, okay. And then you do ratio of these two, I0, ratio of these two, I mean log, do this I0 by I and take then log, take logarithm of this, log of this, then it will be giving you this OD. So, this from this detector is fed into some computer and then computer gives you OD or maybe absorbance. Now, what you do? You plot this side OD versus maybe wavelength, then it will be giving you something like this. This is called your absorbance spectra. That is the spectra, it is the ordered arrangement of OD as a function of wavelength, and this is your absorption spectra because of since I0 is more than I, therefore, this I is less means this is your IF, it is less than I0 means there is some, I mean absorption has taken place, absorption of radiation has taken place. Okay. Now, there is another term, that is transmittance, that is the amount of light that is transmitted, okay, that you can also use. There is another way. So, in certain apparatus, in certain instrument, or maybe nowadays in all the instruments, you can have maybe transmittance mode of plotting or maybe absorbance mode of plotting, okay. And the point is that you see that this particular equation works for monochromatic light. Why? Because this E lambda is very characteristic of the molecule and also it depends on lambda. Therefore, monochromatic light is a must. Okay? That means at different wavelengths you can have different E lambda values. Okay. So, this is about Beer's law, and this is about the simplest schematic, very simple schematic of an absorption spectrometer. Okay. Next, so what is absorption spectra? An absorption spectrum is a plot of absorbance versus wavelength. Okay. Absorbance can be plotted as a function of wave number or frequency as well. Okay. So, absorbance versus wavelength. So, therefore, this is absorbance versus wavelength. So, this is called the absorption spectra, and this absorption spectra is very characteristic of the molecule. Sometimes two molecules may have very similar absorption spectra. That means that light absorption wise they behave in the same way as, I mean these two behave in the same way. Now, absorption can be atomic absorption. Atomic absorption means various atomic, I mean levels are there. Atomic levels means atomic energy levels are there. Atomic in the sense like, say, think of your Bohr's model. So, these are the outer levels. So, this is one level, there is another stationary level, there is another. So, absorption of energy and giving rise to, I mean this may happen in atomic level, I mean atomic quantized level, or maybe in case of molecular absorption it may be it is associated with, for your molecular absorption it is associated with electronic, vibrational and rotational motion that I already have discussed. That means molecules are associated with a number of levels characterized by various motions. One can be electronic, the other can be vibrational or the rotational. So, depending on the frequency that you are providing, the molecule will absorb that particular depending on the frequency and also depending on the availability of the stationary states, molecules will absorb energy and correspondingly absorption spectra is obtained. Okay. So, that is why so for molecular absorption these three motions are important, and for atomic absorption maybe electronic transition between the various atomic levels, this electronic levels are involved. Fluorescence spectroscopy. What is fluorescence? So, till now we have talked about this absorption, and in the very beginning of the last lecture I told that this general optical spectroscopy can be absorption spectroscopy or maybe it can be emission spectroscopy. Okay. So, one is absorption spectroscopy, another is emission spectroscopy, and we talked about this absorption spectroscopy already. Now, we want to start with fluorescence spectroscopy. Okay. Now, fluorescence spectroscopy, or better to say luminescence spectroscopy. Luminescence spectroscopy means anything, any energy, it is as a result of luminescence. If something luminous, then correspondingly if we measure or if we analyze that luminescence light, then it is called the luminescence spectroscopy. Now, interaction of photons with molecules result in promotion of electron from ground state orbital or ground state orbitals to high energy levels. Okay. Interaction of photons with molecules, because interaction of photons means radiation and with molecules, that is radiation matter interaction results in promotion of electron from a lower energy level to a higher energy level. Okay. And the molecule, this promotion, how it is depicted. So, you have the molecule, then you put H nu, that means you are allowing this molecule or matter radiation interaction giving rise to excited, it is generally designated by M star, that is excited in the molecule in the excited state. Okay. Now, since excited state means it is having additional energy compared to the ground level by H nu, generally by H nu or broadly by H nu amount. So, it is not a very stable situation, it may be a metastable or maybe it may be an unstable state. So, what it will do? It will try to come back by releasing this excess energy, that is reducing its energy by giving out this excess energy and come back to the ground level or come back to the original level or to some lower level. Okay. So, if it comes back to the lower level by giving rise to certain radiation, then it is called luminescence. Okay. So, molecules in the excited state do not remain there for a long time. That means it has got a finite life in the excited state. Finite life means it stays, the molecule, this M star has got some finite life, it remains as M star for some time. Okay. Now, in solution spectroscopy, we do not say it like we do not talk about a single molecule, but we talk about a collection of molecules. Collection of molecules means life, excited state life means we generally talk in terms of how much of fraction is deactivated due to after a lapse of certain time. From that we calculate its lifetime. So, it is not the lifetime of a single excited molecule, but it is the lifetime of an assembly of molecules. That is a collection of molecules. It is an ensemble concept. So, molecules in the excited state do not remain there for a long time, but spontaneously it comes back to a stabler ground state. It may be by spontaneous fashion or via some induced mechanism, and the process is called the relaxation. That is, it relaxes. So, you excited it. So, this is called your excitation. Then it comes back. This is called your, maybe it is giving rise to some radiation. It is called the relaxation. It relaxes to the lower level, giving rise to some radiation. So, this process is called the luminescence. This process is called luminescence. It is a general term. It is not just simply fluorescence. It is called the luminescence. Now, this relaxation process may occur via collisional energy transfer, may also occur via collisional energy transfer. That means this excited molecule, say this is your excited molecule. Okay. So, suppose this molecule, excited molecule, so nearby to this excited molecule there is another molecule, or maybe there is another solvent molecule. So, what will happen? Because of the thermal motion, these two will collide, and as a result of which, this due to collision, this excess energy is transferred from here to here, from here to here, okay, and it comes back to the ground level and it remains maybe in the higher level. Because we are interested about this, so we do not take care, we do not care what is happening to this, okay. So, via collision the energy is transferred to the solvent, or maybe it may be a second molecule. This one may be a second molecule to which this excited molecule is transferring energy. So, this transfer of energy may not lead to radiation. So, therefore, it may be non-radiative energy transfer which does not lead to any radiation out of it. Okay. But there is other possibility that this excited molecule, as I told you, that it does not only make collision with the second molecule or the other molecules, but it may undergo deactivation spontaneously to this, giving rise to some radiation. That is, excess, this excitation energy is given as radiation. We get some radiation, it goes back by spontaneous means or maybe by induced means. So, therefore, when it gives rise to radiation, that means we get luminescence. So, therefore, this process is called luminescence, and fluorescence is a specific type of luminescence. Why I told a specific type of luminescence? Because certain quantum restrictions are there, certain restrictions are there. Okay. Now, when we talk about specific type of radiation, then the point is we must clarify it. Why it is called some specific type of radiation? Now, these electronic states are characterized by overall spin of that particular. So, it may be triplet, or it may be singlet, or it may be doublet. Suppose there are two electrons like this. This is one case, this is another case. Then this is called your singlet, and this is called triplet. So, total spin multiplicity 2s plus 1, 3, here it is 2s plus 1, it is called singlet. So, if now, since it is a radiative transition, that is m star to m this way. So, m star means one level, m means another level. If it is singlet to singlet, or maybe triplet to triplet, that means initial state singlet, two final state singlet, that is if it is a singlet to singlet transition, or maybe if it is a triplet to triplet transition. And during that process, during that singlet to singlet transition giving rise to radiation, or triplet to triplet transition giving rise to radiation, then this is called fluorescence. So, why specific type? I guess now it is clear that when the initial spin state and the final spin state, these two are identical, singlet to singlet or triplet to triplet, then it is called the fluorescence. This is called fluorescence. Okay? And there is an allowed transition, because spin multiplicity, spin state conservation is there, that is why it is an allowed process. It is a spin allowed process. Spin allowed process. Okay. So, that is why it is called a specific type of luminescence. So, any luminescence cannot be called as fluorescence. So, if there is a luminescence, then we have to analyze whether it is through singlet to singlet or through triplet to triplet. So, there are various diagnostics. You may question. So, if this is an additional restriction, then how one can decide about whether this is fluorescence or something else? Of course, there are diagnostics which will allow you to know whether it is fluorescence or else. Okay, so therefore, M stat to M, singlet to singlet or triplet to triplet with radiation is fluorescence. This is again a typical diagram. We already have shown this in our earlier lecture, but again let us talk in terms of luminescence and fluorescence. So, think that these E0, E1, E3, these levels are of similar spin multiplicity. Say for example, these three are singlet, okay, singlet multiplicity. Okay, basically this is your electronic state. I am talking about the electronic state. Okay. So, in this particular case, you see this absorption process takes place between these two singlet states or maybe these two singlet states, and emission process, if this is an emission process, I mean if emission is coming out from here or maybe from here, then that maintains the conservation of spin states, initial spin state and the final spin state. So, initial spin state is, this is your initial state after excitation. So, initial state to final state spin state is conserved, spin multiplicity is conserved, therefore, this will be your fluorescence. Okay. So, this is a more general diagram. What is that? This is excited state level, this is your ground state level. Okay. Forget about this fluorescence lifetime in nanosecond, I will come to that in some appropriate discussion. Just this is your absorbed excitation light, you see that it is shown in blue, and this is emitted fluorescent light, it is shown in red. Okay. And this squiggly arrow has got certain significance. It is related to some famous rule, Kasa's rule, that emission always originates from a level of the this lowest excited level, although there are certain anomaly to that, certain breakdown of that law. There are instances where this law is not violated, but right now we are not interested into that. Now question is, why it is shown blue and why it is red? Because you do excitation to some higher level, then quick deactivation between these upper electronic levels because of certain restriction within the molecule, certain characteristics within the molecule. What happens that this excited state is quickly deactivated to the lowest excited level, and from that fluorescence light is coming out. Again, think in this way that these levels are singlet, and generally ground state is singlet for most of the molecules. But there are examples. I mean one example is oxygen, its ground state is triplet. Anyway, so emitted fluorescence is red means its energy is less, because this much of energy has been lost because of this non-radiative or maybe quick vibration or relaxation. So, this excess energy is given to the surrounding bath as you know heat. Okay, here is it is also shown in the similar way, emitted fluorescence light, and this is the absorbed excitation light. So, energy is increasing this way, and this is your, of course, this is your ground state. Okay, and you see that here, if this is singlet, this is singlet, so singlet to singlet spin multiplicity is maintained, therefore emitted light is fluorescence. Okay. So, this way, you know, this way diagrammatically you can designate a fluorescence process, okay, a fluorescence emission, okay, or luminescence, okay, means you can designate whether it is fluorescence or else. What is else? I'll come to, you know, in later on. Okay, so this is your diagrammatic representation. Now the point is, since you would like to measure or we would like to study fluorescence, we need to have some instrument. Okay, like absorption spectrophotometer, we need to have an instrument which you know has the capability of measuring emission. Now, the basic difference between an absorption spectrophotometer and emission spectrometer is that in case of absorption spectrometer, you have a light. What you have to do? You have to pass through the sample and then you measure the transmitted light. But here what you have to do is you have to use the light as an excitation source. That means you have to excite the molecule, then whatever light is coming out of that excited molecule, that light you have to analyze. Okay. So, therefore, you have a lamp, then there is one optics like lens, okay. There is one optics like lens that will allow the light to enter into a dispersion medium. Generally it is called the monochromator, okay, a dispersion medium. Why dispersion medium is required? As I told you that this lamp, this light source, this is generally xenon lamp, high pressure xenon lamp. It has got a huge spectra that is that encompasses both UV and Vis region up to say 900 nanometer from 200 nanometer, okay. So, it has got a huge span, but the point is, since we are dealing with specific energy levels, energy levels like say these two specific level or maybe some other specific energy levels, we need to tune this gap, this excitation gap. So, we need to tune this excitation gap means we need to have a device that will allow the system or allow the sample to get different excitation. That means we keep on changing the excitation source and we correspondingly measure the amount of light that is coming out of this this sample. Of course, the point is this emitted light can have other complications that I am coming to in a minute, but the point is that this monochromator M1, this has the capability of, this monochromator M1 or this dispersion medium has the capability of selecting certain frequencies to enter into the sample. Okay, the sample will get that excitation and then it will emit. So, emission will take place in all possible directions. It is not that it will happen only in the path of light, it will not happen like that. So, therefore after it is getting excitation, the sample will emit. Now, the point is, if we go back to this slide, you see that the emitted light will have not only one frequency, but several frequencies depending on the complications in the energy levels, associated energy levels. Okay, associated energy level means whether there is involvement of vibrational levels. Of course, vibration levels are involved. Therefore, your emission, what will happen, your emission will have not only on a frequency, but other frequencies are also there. That means emitted light will have some spectral feature, I mean it will have more than one frequencies. So, then what we do? With the help of another dispersion medium, we measure different components. I mean, using this dispersion medium, allow each frequencies one after another to PMT, and then PMT measure. PMT means it's a detector, photomultiplier tube. It's like a photo cell kind of thing, means more light, more current, so more signal that way. So, this monochromator selects all the possible, identifies all the possible frequencies present in the emitted light, and that way it creates it records the spectra, which is called the emission spectra. Unlike absorption, it is called the emission spectra. Now, if you look at the this particular diagram, you will be finding that this excitation light and the detector, these two are perpendicular to each other. You see, this one and that one is perpendicular to each other. Unlike your absorption spectroscopy, this is your sample, this way light enters, this way light goes, this is your detector and this is your source. This is the simplest of the lot. But in case of your fluorescence, what is happening, that you have got your sample, you have your excitation source this way, and emission is collected at 90 degree. This is detector, this is source. Maybe there is monochromator here, there can be monochromator over here, but this is the simplest diagram. Now, the question is why this your PMT or the detector is placed 90 degree, means at a geometry which is 90 degree with respect to the incident light. The point is that when light falls onto the sample, when light hits the sample, there is possibility of scattering, okay, in all directions. But if we collect signal at 90 degree with respect to your excitation source, I mean this way, okay, this way, this is your excitation source, this is your detector, and this one is your sample. Then what will happen, that there will be scattering, but scattering will be minimized. Okay. One thing that may come in your mind, that why do not we use this collinear geometry like your absorbance spectrometer? Why not collinear geometry? Because in this case what will happen, that this is your excitation source, say this is your excitation source, this one is your excitation source. Okay. So, what will happen, that if you keep your detector over here, this side, then through your sample, okay, the excitation light will also enter into the detector and complicating the measurement. Okay. So, that means in this case what will happen, that the absorption signal along with emission signal will be there. I mean this signal will be contaminated with the absorbance signal as also emission signal. So, in order to get rid of that, we keep the detector 90 degree with respect to excitation source to minimize scattering and avoid excitation source. But that does not mean that excitation source is completely blocked. No, it cannot be completely blocked, but you can minimize as much as possible. At 90 degree angle, the excitation light is scattered into the detector to a least extent. Okay. Now here so ultimately this is your source, then this is slit to control how many photons you are allowing to the sample. Okay. Then this is your diffraction grating, I mean this is your monochromator 1, then another slit again to control the number of photons, then sample. Okay, sample means you have got some fluorescent material which absorbs radiation and then gives rise to fluorescence. Then there is slit, then this is another dispersing system, then finally to the detector. Okay, so this is the typical diagram of a fluorimeter which measures the fluorescence intensity. It does not do your like log I0 by I, that is OD expression. No, it does not do OD, it directly measures the intensity. It does not do OD. OD, no, it does not do OD for fluorimeter. Of course, in this case your fluorescence cuvette will be transparent in all, I mean all 4 windows are transparent, because this way excitation comes and you have to collect this way. So, therefore, this surface or this window has to be transparent and this window will also have to be transparent. Therefore, this 90 degree, I mean those 2 perpendicular windows are to be transparent. The same way these 2 are also transparent. So, this cell is different from your UV cell where only these 2 windows are transparent and these 2 may be frosted. But the point is you may use a fluorescence cuvette for your UV measurement, but no UV cuvette can be used for your fluorescence measurement. So, what we get, again think of this diagram, this one, blue red, excitation blue, emission red, excitation violet, emission yellow. Okay. So, the emitted light has following characteristics. Okay. What are those? This light is usually of longer wavelength. Longer wavelength means lower energy, okay, compared to the excitation light. It is very clear, because if you go back to this slide, excitation requires more energy because you may excite to some higher level, then quickly it comes back to the lowest level, lowest electronic level. Remember, these levels may not only be this electronic levels, but maybe these levels are the associated vibrational states of this electronic level. It may be like that. So, you may excite to an excited, I mean excited state in the again in the vibrationally excited state. Okay, that means after absorption of the excitation light, the system goes to a vibrationally excited state of the first electronic level. Okay. Okay, then it means quickly relaxes to the lowest energy level, I mean lowest energy singlet state, and then it gives rise to fluorescence. So that is why the light is usually longer wavelength, lower energy than the excitation light. Next is the emitted light may have many wavelengths which results in fluorescence spectrum. As I told you that the first monochromator sends a particular frequency to this sample, and after getting this excitation, this molecules, excited molecule may emit not only a single wavelength, but in most of the cases multiple wavelengths. That is, that results in emission spectra, and generally emission spectra, if you plot intensity versus wavelength, then maybe it will look something like this. Okay. So, this is your emission maxima, one maxima, this is another maxima, this is the third maximum. Okay. So, this is your emission spectra, that is when we plot with respect to M2 monochromator 2, that is when monochromator 2 is you know analyzing this emission. Okay. Because we have to analyze this light with respect to this excitation source. So, that means in that case when we draw an emission spectra, then we have to have certain information input, that excitation source, I mean excitation say maybe excitation say x nm, that is you excited x nm, and emission maybe from some y1 to y2 nm. This way you have to write. Okay, that will make sure that where you have excited the sample and from which wavelength to which wavelength you have taken the spectra, you have plotted the spectra. Okay. So, this is a the simplest, this is simplest fluidometer which we generally use in everyday spectroscopy, especially everyday fluorescence spectroscopy. Okay. So, therefore, emitted light may have many wavelengths which results in fluorescence spectrum. Now, like this OD business, log I0 by I, Beer's law, luminescence intensity can also be described or quantified in terms of quantum yield, a term which is called quantum yield. Now, what is quantum yield? Quantum yield is like, think of yield of a reaction. Suppose we have used say 100 say grams of certain substance, 100 grams, and say out of 100 grams 90 grams is used up in certain reaction, in a particular reaction, then what we say that usage is 90%. So, in the same way, similar way, luminescence quantum yield Q is expressed, means of course it is luminescence, forget about any other complication. If there is a simple luminescence case, then quantum yield is the ratio of the number of photons that is absorbed, that is in, to the number of number of photons out to the number of photons in. I mean suppose you have sent 100 photons and you are getting say 80 photons, that means its quantum yield will be 0.8. Okay. So, this way we can quantify whether a substance is a good fluorescer or emitter, or a substance is a weak emitter, because in case of emission spectroscopy, main concern is your how much of photon we can get out of a given number of input photons. Okay. So, luminescence quantum yield is the ratio of the number of photons out to the number of photons in. Okay. So, quantum yield is a very important characteristic, and this quantum yield I will come to this in more details, that quantum yield is very much dependent on the wavelength, means where you are exciting, also of course the nature of compound, solvent, temperature. There are various factors which may control the value of quantum yield Q. Okay. So, therefore, quantum yield is a very very important term in, especially in fluorescence spectroscopy. So, as I told you that initially I talked about luminescence or emission. I did not want to use the term fluorescence directly, okay. And I said the term fluorescence is a special or a specific type of emission or luminescence. It has got a specific characteristic, like the involved states will maintain spin multiplicity. I mean, spin multiplicity is conserved between the initial state and the final state, that is for fluorescence. But suppose a situation arises where your initial state spin multiplicity and final state spin multiplicity, these two are different, then what will happen? So, this is another type of emission, okay. This is another type of emission which occurs when the involved state, it is of course a radiative process, involved states are having different spin multiplicity, that means singlet to triplet or triplet to singlet. If that happens, that is, it is not a spin allowed process, then it is termed as another type of luminescence called phosphorescence, okay. So, let us come to a diagram that will be more, more informative, okay. So, think about this ground state. This is the original ground state of the molecule. This is S0, this is S1, that is first singlet state, this is second singlet state, okay. This is absorption process, that that is transition between ground state to S2 or ground state to S1, that is S0 to S1 or S0 to S2, okay. These are the associated vibrational levels, and of course there is another level close to this singlet, there is another level which is called whose multiplicity is different from this. This is singlet, this is triplet, 2s plus 1 equal to 3, this is 2s plus 1 equal to 1. These are the associated vibrational levels. So, what happens is that when you excite the sample maybe to S2, then maybe it is a vibrationally excited state or may not be vibrationally excited state. When it is vibrationally excited state, it relaxes to S2, I mean lowest, means to this level, I mean it relaxes to this level where I mean it is your V0 level, okay, or the lowest level. Then similar is the case for here, that it is the only, I mean the excitation may be here and then it can come back to this level. Similar may happen over here. These are called the vibrational relaxation, okay. Now the system means, suppose if you excite to S2, then maybe system what will happen, that system may transfer from S2 to S1 because S1 is the lower level than S2, and then transition may take place. I mean this transition is called some internal conversion, I mean called internal conversion. Now then again transition may take place from here to here, which is called fluorescence, and maybe here to here another fluorescence, here to here another fluorescence. So, you will be getting a number of frequencies. So, that means you expect a fluorescence spectra. But suppose the situation is such that this S1 to T1 transition is somehow allowed because of some mixing factor. All of you perhaps heard about the term spin orbit coupling. Because of mixing, what is happening, that maybe this triplet has got some singlet character and this singlet has got some triplet character. Therefore, this transition is partially, I mean this transition from here to S1 to T2 is say partially allowed. then some population will be built up. I mean, some excited molecule will also be found over here. Some excited molecules will be found over here. So now you get some population over here. Now if this happens that some radiative de-excitation occurs from here to here, then we will be getting some emission. But you see that difference from fluorescence to phosphorescence, difference between fluorescence and phosphorescence, I mean this is called phosphorescence because it is a spin forbidden transition between T and S. See, this gap is less, this gap compared to this gap. So that means fluorescence occurs at a redder or red wavelength compared to the excitation source. Phosphorescence occurs at still red, I mean further lower energy region of the spectrum. Okay. So if it happens say in the yellow region, then phosphorescence from the same molecule will occur in the maybe in the red region, or maybe in some cases it is found to occur in IR region. Therefore, so that is the difference. I mean phosphorescence energy, I mean this frequency is lower compared to fluorescence frequency, and phosphorescence is a spin forbidden process. Okay, since it is spin forbidden, since this process is not a very allowed process, therefore population, I mean population wise the system will remain here for longer time, therefore its lifetime will be more. That I will discuss in some other context, that is in the context of lifetime of radiative lifetime of molecule. Okay, so that I will discuss later on. So therefore this is another specific type of emission which is called phosphorescence. So in summary, what do we get? That we talked about light absorption. We talked about light absorption, and light absorption means when there is light absorption, there is excitation. Excitation means molecules are excited from the lower level to the upper level. Okay, from lower level to the upper level. Okay. Now, if lower to upper, then there is a possibility that it will come back through radiation. This is called emission. I am not telling it is fluorescence, it is emission. To talk about clearly whether means more clearly we can say, means we should say that we have to think about whether the involved states are of same spin multiplicity or different spin multiplicity. Okay. If same spin multiplicity, then it is for sure fluorescence. Different multiplicity, it is phosphorescence. So general term is luminescence. And to analyze such luminescence processes, to analyze such luminescence, I mean luminescent light, we need to take help of an apparatus, okay, that is called a fluorimeter. Okay, it is different from an absorption spectrophotometer, that it relies on the fact that its excitation source, I mean excitation path and the detection path, these two are perpendicular to each other, okay, to minimize scattering. Now importantly, fluorescence spectra, the fluorescence spectra of molecule is very much dependent on the excitation light. If your excitation light is changed, then maybe it has been found in many cases that fluorescence spectra or maybe luminescence spectra is altered. Okay. So therefore it is very important. That's why when we represent some fluorescence spectra, it is basically an intensity versus wavelength plot with respect to M2, that is monochromator 2. Then we always have to write excitation source and then emission is taken from which wavelength to what wavelength. Okay. So and these fluorescence spectra are very characteristic of the system of interest, and this fluorescence spectra and or maybe better to say luminescence spectra, these are very characteristic of the system of interest. Very characteristic of the system of interest means if there is a change in system of interest plus also on the environment of the system. Suppose if you have the same molecule, but if you are putting in different environment, suppose one in water, another in say in other like say in hexane, or maybe in some other situation, maybe inside protein, then this luminescence spectra has been found to have a profound change, profound alteration. So, looking at these profound alterations in the luminescence spectra, one can track various details of the processes that are going on and various causes of such alteration. So, that is all for today. So, we will have more discussion on this luminescence, fluorescence and other issues in the forthcoming lectures. Now, in our next lecture we will take up the fate of a molecule after absorption, means what are the possibilities that when a molecule absorbs energy, what will happen to this molecule, what happens, whether it undergoes some chemical, some reaction, or it undergoes some physical process, like emission is a physical process, photon emission is a physical process. So, means there could be various things that may happen, although I have not I have not told till now, I have not told anything about that in detail. So, we will take up that in the next lecture. So, till then have a nice time. Thank you.